In the last video, we introduced the following state transition equation. It told us if we have a distribution of where we think we are at time step n, okay, where u of n is a probability distribution over our states, then if we multiply it times our probability transition matrix, we can see how that probability flows into the next step. Okay. So again, our u of n is some sort of vector that tells us the probability the system is in, let's say, state I at time step n. Okay, so here we might have u of I of n. Okay, so one particular value. All right. Now this equation is actually very useful because it can be generalized without having to go one step at a time. So how do we do that? Well, we can sort of take it and work backwards. So one thing that we can do is we can say, well, u of n plus 1 is equal to p transpose. And instead of u of n here, we're going to say, well, we know u of n is equal to p transpose times u of n minus 1. Okay. Likewise, we know, so let's just write that down and be a little bit more clear. So we know that u of n is equal to p transpose times u of n minus 1. And that's just applying the same equation. All we're doing is changing the index right here. So it's n minus 1 to n. Likewise, we know u of n minus 1 is given by p transpose times u of n minus 2. And u of n minus 2 is equal to p transpose times u of n minus 3. And this keeps going and going and going until we finally get to u of 1 is equal to p transpose times u of 0. Okay. So what we can start doing is substituting in these values all the way down. Okay. So when we do that, we've already substituted in u of n, right? Now we can substitute in u of n minus 1, which we know is p transpose times u of n minus 2. Okay. Now, these p's are just matrices that are doing the multiplication. So in fact, we can pull them out. So one way we could write this is p transpose times p transpose times p transpose times u of n minus 2. Okay. And again, we can substitute in u of n minus 2. And hopefully you can see that we just get p transpose 4 times times u of n minus 3. Okay. And so this keeps going and going and going. Yeah. So if we take this all the way down to u of 0, what do we end up with? So we have p transpose times p transpose all the way to p transpose. And let's just pretend we're going to have a whole bunch of these. The question becomes how many. All right? And so we're going to multiply all these p's times u of 0 at some point. Okay. So how many do we think there'll be? So we started off here where we had one step transition. We had p to the first power. When we made it from n minus 1 to n plus 1, we had 2 p's, right? So the little hint here is 1 plus 1, right, 2. If we go from n plus 1, but we pretend we're starting off at n minus 2, that's 3 p's, right? That difference, okay? So now we keep adding 1, and how many of these p's are we going to add? Well, we're going to add n of them, okay? And so it ends up that we have n p's plus the original p that we started with. Okay? So one way that we can think about this is we can think about this as p transpose to the n plus 1 power times u0. And so this is going to be a more general form of the equation. And in fact, let's take one more step. We're actually going to simplify it, because this is a little bit weird. Normally you don't write things that way. The way that we're going to simplify is we're going to get rid of that plus 1, because we don't really need it. And so it ends up that this is the same thing as just writing at time step n, the probability distribution is just given by p transpose to the n power times wherever we started off with. Okay. This is a very useful equation, because what it tells us is we don't have to go through this process of saying, all right, I know u0, so that allows me to calculate u at time step 1, which allows me to calculate u at time step 2, right? And to keep doing this, if I asked you what is u of 1,000, okay, before you'd have to keep multiplying p times a vector and then take that vector and multiply it times p, and then take the result of that and multiply it times p. You'd have to do that 1,000 times. But now, what I'm telling you is, if you want to figure out what u to the n is, let's say at time step 1,000, all you have to do is take p transpose to the nth power. Now, for those of you who might remember your linear algebra, there's a nice little property that we have, which is a matrix transpose to the n power is the same thing as a matrix to the n power transpose. So we can simply rewrite this as p to the n transpose times u0. So I know it was casting a little bit of a funny light, but just in case there's any confusion, there was an n power up here.